Hello and welcome to TI Precision Labs. TI's Precision Labs video program is a comprehensive online curriculum for engineers. This video covers the basic questions you may have about digital isolators. More videos and topics can be found by going to ti.com/Precision Labs. What is a digital isolator? Galvanic isolation is a necessary form of protection for all electronics that interface with humans or other circuits in the presence of possible high-voltage events. In the case of human safety or even electronic protection, a high-voltage event can range from tens of volts to kilovolts. Over the past several decades, the technology used to isolate circuits has moved from optical-based optocouplers to silicon-based, with the digital isolators being the preferred choice for more and more designers. This video will focus predominantly on capacitive-based digital isolators. A general introduction to isolation technologies can be found in the Precision Lab titled, What is Galvanic Isolation? This Precision Lab will answer the following questions. What is a digital isolator? How are capacitive digital isolators built? How does an edge-based digital isolator work? How do on-off keying or OOK digital isolators work? Which digital isolator architecture is best for my design? Let's get started. What is a digital isolator? Digital isolators are integrated devices used to isolate digital signals and transfer digital communication across an isolation barrier. Because digital isolators are working with a pre-digitized data stream, they typically follow the ADC in a system, sitting between the microprocessor and FPGA that are at different supply levels, or between interface communication boards with shared backplanes. In this example, the digital isolator is protecting the MCU data line from the output digital to analog converter in a 4 to 20 milliamp loop. When looking at a use case like the one shown here, it is clear that when using a digital isolator, an isolated power supply is needed as well. More details on power supply design for isolators can be found in the Precision Lab video titled, How to Design Isolated Power for Digital Isolators. Let's now take a closer look at the digital isolator itself. How does a digital isolator work? A pin diagram of a typical digital isolator is shown here. It consists of two isolated supplies, VCC1 and VCC2, two grounds, GND1 and GND2, and input and output pins on either side referred to the respective grounds. The input signal is modulated through a transmit IC and then passed through a high voltage capacitive barrier and across the connecting bond wire to the receiving side IC. Ideally, digital inputs and outputs are identical when an input signal is applied. As mentioned earlier, digital isolators are most commonly used with isolated power supplies and separate grounds, which is also useful in preventing ground interference and noise currents from power supplies. Digital isolators use CMOS or TTL logic switching technology and have specified default output states of high or low that can be found in the device functional mode section of the datasheet like the one shown here. As seen in the table, if inputs are disconnected or VCC1 is disconnected, the output will transition to a logic state high. This behavior is called a fail-safe high. Alternatively, some devices will go low in a disconnected state, called a fail-safe low. This behavior is defined to help prevent error codes in the event of a supply outage or brownout condition. Logic levels for the digital isolators can range from 1.8 to 5.5 volts for both supplies, VCC1 and VCC2, though some devices may support a larger supply range. Because the isolator is based on two separate internal ICs, two different supply voltages can be used for each side of the digital isolator. Now that we have a high-level understanding of how the digital isolator works at a functional level, we will discuss the internal structure and architectures for digital isolators. How are capacitive digital isolators built? Capacitive digital isolators use silicon-based dielectrics built on CMOS technology and consist of two separate integrated circuit or IC chips, an input circuit and an output circuit, connected through bond wires and high-quality, high-voltage resistant mold compound. A cross-section and an X-ray of the digital isolator are shown. The insulator of a digital isolator circuit can be either a single or double silicon dioxide capacitive barrier, which can withstand extremely high voltages by design. The capacitive-based isolator is constructed of the highest dielectric strength material in the semiconductor industry and is manufactured in a closely controlled clean room wafer fab, making part-to-part variation minimal. Because of the closely controlled manufacturing environment and the quality of the silicon dioxide dielectric, the key contributors to isolation performance are the technology itself and the design architecture. Capacitive isolators typically employ two primary modulation architectures, on-off keying, or OOK, or edge-based. Both names describe the timing schemes used to trigger an output change. How does an edge-based isolator work? With an edge-based digital isolator like the one shown here, data transmission is initiated with an input pulse of specified duration. The I/O channel consists of two internal data channels, a high-frequency channel with a bandwidth from 100 kilobits per second up to 25 megabits per second, and a low-frequency channel covering the range of 100 kilobits per second down to DC. A single-ended input signal entering the high-frequency channel is split into differential signal via the inverter gate at the input. The capacitor-resistor networks then differentiate the signal into transient pulses, and decision logic at the output of the high-frequency channel comparator measures the durations between signal transients. If the duration between two consecutive transients exceeds a certain time limit, as in the case of a low-frequency signal, the decision logic forces the output multiplexer to switch from high-frequency to low-frequency channel. Low-frequency signals are pulse-width modulated with the carrier frequency of an internal oscillator, creating a high frequency capable of passing the capacitive barrier. The oscillator is used to set the timescale of the DC PWM channel with a time base typically in the tens of nanoseconds. PWM communication is then packetized with the smallest possible packets being above the oscillator frequency. The edge-based isolator is designed such that this oscillator frequency will not be reflected in the output spectrum. As the input is modulated, a low-pass filter is needed to remove high-frequency carrier from the actual data before passing it on to the output multiplexer and to the output pins, thereby recreating an electrically isolated version of the digital input signal. How do on-off keying digital isolators work? In the on-off keying or OOK architecture, the incoming digital bit stream is modulated with an internal spread spectrum oscillator clock with a frequency that operates outside the usable data rate of the device. This clock frequency is used to generate OOK signaling, such that one of the input states is represented by the transmission of a carrier frequency and the other state by no transmission. This modulated signal is coupled to the isolation barrier and appears in attenuated form on the receive side, which consists of a preamp to gain up the incoming signal followed by an envelope detector. This serves as a demodulator to regenerate the original digital pattern. The transmit and receive signal conditioning circuits are used to improve the common mode rejection of the channel, resulting in better common mode transient immunity, or CMTI. Which architecture is best for my design? One of the primary benefits of the edge-based modulation scheme is a lower power profile than the OOK architecture. This is because the edge-based modulation isolator only passes a signal across the isolation barrier during data transition or edges. This results in a significantly lower power usage than the OOK architecture, which is in a continuous state of sampling and transmitting the modulated input across the barrier. Because of this continuous transmission, the OOK architecture requires significantly more power than the PWM-based edge-based architecture. Are there specific challenges and benefits to these architectures? Well, there are trade-offs. For the edge-based architecture, once a data signal is initiated, there is no further sampling of input and output states. This does create a risk of an error in the case of a brownout or data signal failure, and therefore requires an integrated refresh circuit to mitigate the risk of errors under these conditions in order to reinforce the input state on the output. In the case of the OOK scheme, the continuous sampling of the input in the event of an unintended supply or input signal change will show no errors at the output. While the edge-based architecture features specific power benefits due to its sampling scheme, we mentioned earlier that the signal conditioning circuits in the on-off keying modulation scheme offer inherent noise and transient response benefits with much higher CMTI and the added benefit of higher data rates. So which capacitive digital isolator topology is really the best for your design? In addition to the critical isolation specifications, when considering each architecture, just remember to consider the additional design priorities of power versus data rate, highest possible common mode immunity, and managing for error conditions to help determine the best fit for you. This completes our introduction to digital isolators. We discussed that digital isolators are used to pass digital signals across the isolation barrier and require isolated power and grounds. Capacitive isolation is achieved using silicon dielectric, the highest dielectric insulation material in the industry. That there are two primary architectures used for capacitive digital isolators, edge-based or OOK. The key differences between edge-based and OOK-based capacitive digital isolator designs are output state, where both edge and OOK-based digital isolation solutions have a predefined default output, high and low state, found in the device datasheet. Data transfer, where edge-based solutions transmit the data stream across the isolation barrier following an input pulse of specified length using the edges of the input stream to construct the output stream. And OOK-based solutions, or on-off keying, which transmits the data stream across the barrier through a high-frequency carrier, enabling improved noise and CMTI performance. And lastly, power consumption. Edge-based architectures offer lower power and lower data rates, while OOK offers higher power with higher data rates. This concludes the Precision Labs What Are Digital Isolators? Thank you for watching. Please try the online quiz to test what you've learned.
Question 1. Which insulation material offers the highest dielectric strength? Mold compound, polyimide, air, or silicon dioxide? Silicon dioxide offers the highest dielectric strength at about 500 volts per micrometer. The most commonly used digital isolator technologies are optical and inductive, capacitive and optical, or capacitive and inductive. Capacitive and inductive topologies are the most commonly used for digital isolation. True or false? Digital isolators can operate with two different supply voltages for VCC1 and VCC2. True. VCC1 and VCC2 can be operated at different values and still maintain datasheet performance. What are the three key trade-offs to consider between edge-based and on-off keying digital architectures? Data rate, power consumption, and noise rejection are the most common trade-offs to consider between edge-based and capacitive architectures. This concludes TI Precision Labs What is a Digital Isolator? Thank you for watching. Please browse more topics at www.ti.com/Precision Labs.